So hello viewers, welcome to the second part of the SRAM video series. In the previous part, we are trying to figure out the memory operations in our computers and knew the basic operations of SRAM and DRAM. Today I will discuss the working principle of the SRAM memory cell. This is the very important topic of this SRAM video series. So I want to request you to pay attention on this video lecture. So let's start. So let's say we want to understand the read operation first. So we assume that in this memory cell we already stored something here, the Q. Okay, so before going to read, there are a couple of synchronous operations we have to maintain. So first, before read, we have to make bit and this bit bar line high, or you can say the bit lines are both initially floating high. Then we assume Q is 0 and the Q bar is 1. Now word is high. So what will happen? Let me draw this for you. So Q is 0, Q bar is 1, bit and bit bar both 1, and initially word is 0. So when the word is initially 0, those access transistors remains off. So there is no connection between this Q node and the bit. Also same goes for the Q bar and the bit bar. So when the word raised, okay, these access transistors are on now, right? So a path will be created from bit to Q, also the bit bar to the Q bar. Now tell me what keeps the Q remain 0 stable. So obviously the one from this Q bar is keep on this D-on transistor on and the P-on transistor off. So from this output to the ground, the Q remains 0. Now let's come to the bit. Bit will go down also the same time, and the node Q tends to rise in the voltage. So how this will happen? Because you can see here is a higher potential and the Q is in lower potential. Okay, so the current will flow from the higher potential to the lower potential, right? And thus the bit will go down, okay, and Q is tends to rise in voltage. So now at the same time you can see the D-on transistor is also on and connected Q to the ground, right? So if Q keeps increasing, D1 is also trying to pull nodes Q towards to 0. You can see there is a fighting between the D1 transistor and the A1 transistor, right? So what do you think? Who should win? So let me ask you something. When you read something from your memory, do you want to change the state during the reading? Obviously no. So we have to help D1 to win, right? So that it will keep the Q 0, right? So yes, we can do that. That's called the read stability criteria, and we will further discuss the topic in the next videos. And on the other hand side, here the Q bar and bit bar, as there is no voltage difference, so no current will flow from the bit bar to Q bar or the Q bar to the bit bar, and the bit bar and Q bar will remain high. So we can say that when the word line is raised, the bit is being pulled down and node Q tends to rise, and Q is held low by this D1 but raised by the current flowing from the A1. The driver D1 must be stronger then the access transistor A1. Specifically, the transistors must be ratioed such that node Q remains below the switching threshold voltage of the P2D2 inverter, otherwise it will flip the Q bar to 0. So this constant is called the read stability. Okay, you can see the waveform here. The waveform for the read operation are shown here. So 0 is read onto the bit. You can see, observe that Q is momentarily rises but does not glitch badly enough to flip the cell actually. If you connect a probe to the bit line and if you observe that your bit line is become 0 volt, then you can say you successfully read 0 on the Q. Assume that previously Q was written to 1, and if you notice there is no voltage difference on your bit line in your probe, then you can say you successfully read the 1. Okay, now let's go for the write operation. So again, assume that Q is initially 0 and that we wish to write a 1 onto the cell. So for the write operation, we have to also follow some sequential operations, right? So initially for the write operation, we have to keep bit high and the bit bar is low and the word is also low before the write operation. Okay, so now the word is become high. What will happen? Okay, let's draw. So Q is 0, Q bar is 1, the bit is 1 here, and we will keep bit bar 0 and the word is now 1. Okay, so what will happen? After word line raised, this A1 and A2 transistor will be on. So now here the Q is 0 and the bit is 1. We want to make this Q to 1. So that's what we want to write. But how can we do this? Okay, you may think that this time I want to let A1 win and this will flip the Q from 0 to 1. But you can do that because you will design your hardware just once. You can change its property like the sizes once the hardware has been already made. So what is the other way? If we can change the input value of this first inverter from 1 to 0, then we can get 1 at node Q, because for input 0 the D1 will turn off and the P1 will turn on and keeps Q node 1 constantly using the source VDD. So that's why we made bit bar 0, because we can see after turn on the A2 transistor, a potential difference has been created and the current will flow from the Q bit bar through A2, right? But here we will face the same fact from the read operation. This P2 will try to keep Q bar 1 and A2 will help to make Q bar to 0. So again, who should win here? Yes, you are right. A2 should win. That's called the write stability criteria, and we will discuss further this topic in the next couple of videos. So when this Q bar becomes 0, it will make this Q1 and thus it fulfills our write operation. I hope now you understand the both read and write operations. Okay, so here you can see when the word length raised high, the bit bar is getting low and the queue is rising after some time. These pictures are taken from the CMOS VLSI design book written by the Neil H. West and the David Manny Harris. Okay, so that's it for today. Hope you get an idea how the SRAM works. In the next video, I will discuss the read and write stability of SRAM. This topic is very important as it defines will your SRAM work properly or not. So please stay tuned, share this knowledge with your friends, and if you have any confusion, please don't hesitate. Please let me know in the comment section. Till then, take care and bye bye.